Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Now we are discussing last topic in this chapter, that is ionic equilibrium indicators. So the previous lecture we have completed already solubility product and to find solubility product of sparingly soluble salts. Now in this lecture we are going to discuss that is indicators. Last topic in this chapter. After this, we'll discuss summary of the chapter. Then this chapter will be finished. So please listen carefully. This is only theoretical concept from this chapter. Usually it is important for NEET as well as JEE mains. Let us see now. Indicators. So what is an indicator? An indicator is a dye or substance which changes color over a short pH range. So what is an indicator I'm writing here? An indicator is a dye means color, which changes colors over a short pH range. This is called an indicator. It's called an indicator. So in indicator we have 2 points. One is end point and second one we have equivalence point. So we're going to discuss all those things in this lecture. So first one is end point, second one is equivalence point. What is an end point? It is a point at which the reaction between acid and base is observed to be completed. It is an end point. Here I'm writing end point is a point is the point is the point at which the reaction between acid and base is observed to be completed. An acid and a base observed to be completed. That is pH at which an indicator changes its color, at which an indicator changes its color. So this is called an indicator endpoint. So equivalence point is the point at which the reaction between acid and base is theoretically complete. So equivalence point means the reaction at which the acid and at which the reaction between acid and base is completed is called equivalence point, and end point is the point at which the reaction between an acid and a base observed to be completed. This is theoretical concept and this is observed concept. Theoretical concept because we'll observe it theoretically, and whereas end point is the point at which the reaction between an acid and a base observed to be completed. That is pH which at which an indicator changes its color is called end point. So based on theories of indicators, we have two types of indicators. One is Ostwald's theory. Next is quinonoid theory and Ostwald's theory. So please listen carefully. This concept is very important for theoretical questions you'll get from this concept. What type of questions also we'll discuss. So this is the last topic in this chapter, that is indicators. So please note it down. Continuation now. An acid-base indicator is either a weak organic acid or a weak organic base. According to Oswald's theory, an acid-base indicator is either a weak organic acid or a weak organic base and ionizes feebly in solution. Ionizes feebly means very less. The color of its undissociated molecule is different from that of the ions furnished by it in the solution. For example, let us take hydrogen indium, that is high HIN. Indium is IN is the indium. So undissociated indicator of color A changes to H plus and indicator ion B, indicator ion B. Like this you'll get. So an acid base indicator is either a weak organic acid or a weak organic base and ionizes feebly in the solution. Feebly means very less. Continuation now. The actual color exhibited by the indicator solution depends upon the H plus ion concentration. It actually depends upon the H plus ion concentration in the solution. When H plus ion concentration is changed, the color of the solution changes due to the shifting of equilibrium in a particular direction. So when H plus ions concentration is changed in the sense it is replaced, then the color of the solution changes due to this shifting of equilibrium in a particular direction. Next, quinoid theory. Indicators are aromatic compounds. So according to Oswald's theory, indicators are weak organic acid or weak organic base. Whereas here, indicators are aromatic compounds such as benzene that can exist in two mutually interconvertible forms, benzenoid and quinonoid forms. It is forms, FORMS. So these two forms as of an indicator possess different colors and exist at different pH of the solution. Only we have two types of indicators. One is Ostwald's indicators. Next is quinonoid indicators. So quinonoid indicators are nothing but aromatic compounds that can exist in two mutually interconvertible forms. One is benzenoid and there is quinonoid. Benzenoid form is either colorless or of light color, whereas quinonoid has a deep color. When pH changes from one form of indicator changes into another form. So this is called quinonoid theory. Listen carefully. Wherever important, I'll tell you. Till that time, just listen carefully and write the PPTs in your classwork. Next, mechanism of acid-base indicator. So that is phenolphthalein. Phenolphthalein is the best indicator. It is a weak organic acid with complicated structure. It is called higher phenolphthalein. It is a weak organic acid with complicated structure. For simplicity, it can be represented as HPH. HPH colorless changes to H plus and phenolphthalein pink color. It gives pink color. So in acidic medium, it is colorless due to shifting of equilibrium towards left on account of common ion effect. And in basic solution, the equilibrium shifts towards right and it shows pink color. So simple words I'll tell you. If you take phenolphthalein as an acid indicator, so phenolphthalein is an indicator. For acid, it is colorless because the equilibrium will shift towards the right side, towards left on account of common ion effect. And for base, it is pink color. It shows pink color. Means what? The equilibrium will shift towards right side. What happens here, I'll just tell you. Generally, phenolphthalein is colorless. When you keep this phenolphthalein in acidic solution, what happens? And phenolphthalein anyway changes to H plus and pH minus ions. pH minus ions becomes pink color. H plus will be formed. And when acid is when phenolphthalein is dissolved in acid, what happens? It gives more H plus ions because from acid we'll get what? H plus ions. So due to the more concentration of ions, equilibrium will shift left hand side. Equilibrium will shift towards left hand side on account of common ion effect because H plus acid contains H plus and phenolphthalein also contains H plus. So due to this, what happens? Equilibrium will shift towards backward reaction. So backward reaction means formation of phenolphthalein again. And due to this, what happens? The solution becomes colorless. So when phenolphthalein indicator is kept in acid solution, it becomes colorless. And when phenolphthalein indicator is kept in basic solution, base solution, it becomes pink color. So this is the acid-base indicator, very, very important. So what is the color of phenolphthalein? When you keep it in an acid, it shows colorless. What is the color of phenolphthalein? When you keep it in a base, it shows pink color. The pink color confirms the given solution is base, and the colorless solution confirms the given solution is acid. Like this, you have to remember, very, very important. So phenolphthalein is used as an indicator. In acid, it shows colorless, and in base, it is pink color. So when you want to test a given solution acidic or basic, you have to use phenolphthalein. So for the given solution, if the color after adding phenolphthalein, if the color is changed to pink color, the given solution is basic. Or if the color of the solution is colorless, the given solution is acid. And why it is forming colorless in acid? Because the equilibrium will shift towards left hand side, because of in acid also gives H plus ions, phenolphthalein also gives H plus ions due to common ion effect. Due to common ion effect. Whereas in basic solution, the equilibrium shift towards the right side and it shows a pink color. Very, very important this slide. Please note it down. So what is the test of phenolphthalein? In acid solution, it is colorless, and in basic solutions, it is pink color. Benzenoid form of phenolphthalein is colorless and exists in acidic solution. Quinoid form is pink and exists in basic solution, basic medium. So when the medium is made basic, the benzenoid form changes into the quinoid form and the colorless solution develops a pink color. So when the medium is made basic, the benzenoid form of acid, phenolphthalein, changes into the quinoid form and the colorless solution develops a pink color. So this is called mechanism of acid indicator. I hope it is clear. Continuation now. Now, methyl orange is a basic indicator. It is a weak organic base, methyl orange. It is a weak organic base, that is indium hydroxide or methanol, and can be represented as INOH. INOH is yellow color, IN plus is red, and OH minus is colorless. In acidic solution, equilibrium shift towards right, and the concentration of IN plus ions increases. So due to this, it forms red color. And in basic solution, equilibrium shift towards left due to the common ion effect and shows it is yellow in color. So benzenoid form is yellow and exists in basic solution, and quinoid form is red in color and exists in acidic solution. So on the whole, what is the color of methyl orange indicator? So for methyl orange indicator, if you use methyl orange as an indicator, for acid, it shows, if you use methyl orange indicator, methyl orange turns red for acid and it turns yellow for base. It turns yellow for basic solution. So it is yellow for basic solution and red in color for acidic solution. So this is the second indicator. First indicator phenolphthalein, second indicator is methyl orange. So both are very, very important. Please note it down because from these indicators they will ask in the examination. So this is the second type of indicator. Next, when medium is made acidic, the benzenoid form changes into the quinoid form and the yellow solution turns red. So if you test this methyl orange solution into methyl orange, if you add it to acidic solution, it turns the acidic solution red. It turns the acidic solution red because when the medium is made acidic, the benzenoid form changes into the quinoid form and the yellow solution turns red color. Very, very important. Next continuation. Let us consider the equilibrium between the ionized and unionized form of an acid indicator, HIN. So HIN changes to H plus and IN minus. So KIN, the equilibrium constant KIN is equal to concentration of products by concentration of reactants. So this is the product here, H plus ions and IN minus ions. So concentration of H plus ion into concentration of IN minus by concentration of H ion, where KIN is called indicator constant or dissociation constant of indicator. So our H plus is called K ion into ion by IN minus. In this way, you'll calculate K value for indicator constant. Indicator constant. Very, very important. So please note it down. Taking negative logarithm on both sides, minus log of H plus is equal to log Kn minus log of concentration of HN by IN minus. So pH is equal to, the formula for finding pH of the indicators is equal to, pH is equal to pKin into log of concentration of IN minus by concentration of HIN, that is ionized form by unionized form. Very, very important. So pH is equal to pKILN, that is pKIN, that is nothing but uh, dissociation constant, or you can say indicator constant. Log of indicator, IN means indicator, log of ionized form by unionized form. This also they'll ask in the examination. Very, very important. Please note it down. In general, the intensity of a colored solution depends upon the concentration of color imparting species. If the solution contains two colored species, if the solution contains two colored species, then the color of the solution depends on the relative concentration of the color imparting species. When the solution contains two colored species such as HIN, that is indicator, and IN minus, then it is seen that the solution acquires a distinct color of IN minus only when the concentration of IN minus is approximately at least 10 times greater than the concentration of HIN and vice versa. So if the concentration of iron minus is 10 times greater, then only it can show the color difference. Otherwise, it will not show any color difference. Very, very important point. Please note it down. Let us consider now based on these two cases. In order to, for the solution to show color due to iron minus, the minimum ratio of IN minus by HN, concentration of IN minus by concentration of HIN should be 10 times greater. So by this you can say log 10 to the base 10 is 1. So pH is equal to pKln plus 1, means the pH value should increase by 1 unit. At this stage, the percentage of the indicator in IN minus form would be given by IN minus concentration of IN minus by concentration of IN plus concentration of HLN, which is equal to HIN into 100 is equal to 91. 10 by 100, 10 plus 1 into 100, which is equal to 91% color change. However, it is not that much important. Only they'll ask the color changes in the examination. Thus, nearly 91% of the indicator has been present in the ionized form. In fact, pH is equal to pKIN plus, that is pKIN indicator plus 1. So the minimum pH up to which the solution has a distinct color characteristic of Indian minus ions. Indium minus ions, iron minus ions. At pH greater than this value, some more indicator will be present in the ionized form. Thus, pH is greater than or equal to pKIN plus 1. The solution has a color characteristic of iron minus. Case 2. In order for the solution to show color due to HIN, first show it is color due to iron minus, next color due to HIN. The minimum ratio of IN by HN should be 1 by 10. It should be minus 1. pKlin plus log of 1 by 10 is equal to pK indicator minus 1. So it is 9.1 percentage. Anyway, these calculations are not that much important. Thus, nearly 9.1% of the indicator has been present in the ionized form, and similar to 91% of the indicator is present in the unionized form. In fact, pH is equal to pKIN minus 1, the maximum pH up to which the solution has a distinct color characteristic of HN. At pH smaller than this value, some more indicator will be present in the unionized form. Thus, pH is less than or equal to pKIN is equal to 1. The solution has a color characteristic of HIN. The solution has color characteristic of HIN. So please listen carefully. Very, very important commonly used indicators. And here onwards it is important because the theory is and their ranges. And their range. Commonly used indicators and their ranges. Let us see now. Indicator, methyl orange indicator, pH range is in the range of 3.1 to 4.4. Color in acidic medium, as I told you, if the pH range of the acidic solution is the range of 3.1 to 4.4, methyl orange shows red color in acidic medium and orange color in basic medium. And methyl red, if it is the pH range from 4.2 to 6.3, it shows red color in acidic medium and yellow color in basic medium. Phenol red, it is a type of indicator: methyl orange, methyl red, phenol red, thymol blue, phenolphthalein. So phenol red is 6.8 to 8.4. It is yellow in acidic medium and red in basic medium. And thymol blue 8.0 to 9.6. It is yellow in color in acidic medium and color in basic medium is blue color. Similarly, phenolphthalein, 8.3 to 10, that is a pH range of phenolphthalein solution. It is colorless in acidic medium, and a basic medium, it changes to red color. So the pH ranges of all the indicators are given. Methyl orange, what is the pH range? 3.1 to 4.4. What is the pH range of methyl red? 4.2 to 6.3. What is the pH range of phenol red? 6.8 to 8.4. So when methyl orange indicator is added to acidic solution, it turns the solution red color. Simple sentence I'll tell you. When methyl orange indicator is added to acidic solution, it changes into red color. Similarly, when methyl orange of pH in 3.1 to 4.4 is added to methyl iron solution is added to basic solution, it changes to orange color. And similarly, methyl red is another type of indicator having the pH range 4.2 to 6.3. When methyl red is added to the acidic solution, it changes the acidic solution to red color. Similarly, when methyl red is added to a basic solution, it changes the basic solution to yellow color. So this shows the solution is basic. If the color of the solution is yellow in yellow color, the solution is basic. So like these questions they'll ask in the examination. So phenol red, these are the pH ranges of the indicators. 3.1 to 4.4 is the pH range of methyl orange indicator. Methyl red, what is the pH range? 4.2 to 6.3. And phenol red, what is the pH range? 6.8 to 8.4. Thymol blue, what is the pH range? 8.0 to 9.6. And phenolphthalein, what is the pH range? 8.3 to 10. So all these are the common indicators, very, very important, this table. Definitely they'll ask in the examination. Simply they'll ask the question like this. For a given solution, for a given solution, a methyl ion solution having pH range of 3.1 to 4.4 is added, then the solution turns yellow color. Sorry, solution turns orange in color. The solution is acidic, basic, or neutral. So the solution is orange color means basic solution. Like these questions, they'll ask in the examination. So let us see now. Very, very important. Please note it down. So I'll write the question here. Simple. When phenolphthalein, how they form a question? Phenolphthalein indicator having, so the table itself is important, having pH range 8.3 to 10 is added to a solution, to an unknown solution, to an unknown solution, the unknown solution becomes the unknown solution becomes yellow in color. The unknown solution turns, not becomes. The unknown solution turns yellow in color. The nature of unknown solution is, the nature of unknown solution is, they'll ask a question like this in the examination. Option A, it is acidic. Option B, it is basic. Option C, it is neutral. And option D, none of these. Like this question they'll ask. So since we already know, when phenolphthalein solution, phenolphthalein indicator having pH range is added to the unknown solution, the unknown solution turns yellow in color. So it shows when phenolphthalein solution is added to a solution, if the solution turns yellow in color, we can say that is basic solution. If the solution is colorless, we can say that is acidic solution. So answer is basic solution, B option. Like these questions, they'll frame in the examination. So please note down. You can see here. So in this way, you'll get the question. So please copy it on this. So this is about acid-base indicators: phenolphthalein, thymol blue, methyl orange, methyl red. All these are the common indicators which are used for indications. Next, continuation. Next continuation. Next concept. After acid bases indicators, we have another concept called, very important concept. This is also, what is pH metric titration curve? pH metric titration curve is also, they'll ask the only graphs from this. They'll ask graphs from this type of questions, from this concept. So all the graphs are important. So please note it down. In acid-base titration, as the base is added from butyrate to acid, the pH of the solution goes on changing. At the end point, a sudden change in pH is observed. End point means the reaction is completed. A sudden change in pH is observed. So a graphical plot of pH against the volume of base added is known as pH metric titration curve. What is pH metric titration curve? In acid-base titrations, as the base is added from the butyrate to acid, the pH of the solution goes on changing. And at the end point, a sudden change in pH is observed. So this is called a graphical plot of pH against the volume of base added. A graph plotted between pH against the volume of base added is known as pH metric titration curve. pH metric titration curve. Very, very important. So please note it down. The pH color near the endpoint is in titration must fall in the pH range of indicators. Now, selection of indicators for strong acid and strong base. Very, very important. Strong acid and strong base. They'll ask different titrations. Weak acid, weak base, strong base titrations. In the titration involving a strong acid and a strong base, the pH of solution changes from about 3.3 to 10 near the end point. Phenolphthalein pH range 8.3 to 10 and methyl orange pH range 3.1 to 4.4 are commonly used indicators. So for the titration between strong acid and strong base, what are the common indicators we'll use? Phenolphthalein and methyl orange. Phenolphthalein will show the endpoint 8.3 to 10. That is 8.3 to 10. Phenolphthalein in this range, 8.3 to 10. And methyl orange in between 3.1 to 4.4. So the pH is equal to 3 is the equivalence point. This is the theoretical observation. Theoretical point is called equivalence point. And observation point is, this is called observation point. This is called observation point. This is called end point. What is this called? End points. For what is the end point for strongest strong base? What is the end point for phenolphthalein? It is 8.3 to 10. And for strong acid and strong base, what is the end point of methyl orange indicator? It is in the range of 3.1 to 4.4. These end points they last. That is in the range of indicators. pH range of the indicators are nothing but end points. So this is a graph, that is pH values as it is increasing. The equivalence point, it is equal to 3 for strong acid and strong base. What is the equivalent point? It is equal to 3. Titration of strong acid, strong base. And methyl orange is indicator where it shows 3.1 to 4.4. The range of methyl orange is 3.1 to 4.4. You can see the range 3.1 to 4.4. And what is the range of bromothymol blue? It is in the range of 5.5 to 6.5. 5 to 6.5 bromo. So it is approximately 6.5. 5 to 6.5 approximately. You can see the values clearly. And for phenolphthalein, it is 8.3. This is 7 greater than 7. It is 8.3 to 10. Actually, this has been wrong. It is 8 and this should be 10. 8 and 10. 8.3 to 10. So this is the titration involving a strong acid and strong base. So what are the indicators used? Phenolphthalein, bromothymol blue, and methyl orange. Next continuation. In the titration of weak base, and against a strong acid. So the titration value will be like this. Against strong acid, say HCl. Weak base is ammonium hydroxide and strong acid HCl. The end point lies in the acid range 3.1 to 6. For the acid range, it is 3.1 to 6. For methyl orange, the pH range is 3.1 to 4.3. For methyl red, pH value is 4.2 to 6.3. And suitable indicators are suitable indicators. Phenolphthalein cannot be used for such titrations. So we cannot use phenolphthalein for such titrations because the end point should be in the range. So for methyl orange indicators, so for the titration of weak base against a strong acid, the titration of weak base and against a strong acid, phenolphthalein cannot be used as indicator. Only methyl orange and methyl red because the end point lies in the range of acid range 3.1 to 6. 3.1 to 6. So this is the end point range. So please note down with the phenolphthalein, this point is important. Phenolphthalein cannot be used for such titrations. For which titrations? Titration between weak base against a strong acid. These are the observations, indicator observations. So methyl orange, pH is equal to 7, 4.2 to 6.3, methyl red color. Methyl orange shows orange color and methyl red shows red color. Endpoints are important in this. The titration, they'll ask endpoint as well as equivalence point. Next, when a weak acid, say acetic acid, is titrated against a strong base, third case, the pH near the endpoint is 7 to 11. This point is important. So the endpoint is 7 to 11. For 7 to 11 means definitely we'll use phenolphthalein as an indicator and thymol blue. So based on the pH range near the endpoint only, we will select the indicators. So if you see the previous slide, let us go for previous slide. So in the previous slide, if you take into consideration, the pH acid base range is 3.1 to 6. So 3.1 to 6 means definitely we will select only methyl orange and methyl red. We'll select only methyl orange and methyl red. So in the first case, if you take in the first case, what happens to the pH? So titrations involving 3.3 to 10. So the titration involving strong acid and strong base, the pH of solution changes from about 3.3 to 10. So what are the common indicators we can use? We can use methyl orange, methyl red, and phenolphthalein. Phenolphthalein, methyl orange, phenolphthalein, and bromothymol blue as an indicators. Second case, what are the indicators we are using? Since the acid range point is 3.1 to 6, that is weak base and strong acid. So we can use only methyl orange and methyl orange and methyl red only as indicators. Phenolphthalein does not show any color. That's what, because based on the pH range of acids and bases also we have to think. And when a weak acid, now in this case, what happens? When a weak acid is titrated against a strong base, example sodium hydroxide, the pH range near the endpoint is 7 to 11. Since it is 7 to 11, we cannot use methyl orange and methyl red. Only we can have to use phenolphthalein, thymol blue as suitable indicators. Methyl orange cannot be used for such titrations. We cannot use methyl orange for such titrations where we have the end point is in the range of 7 to 11. So initially change in pH is due to free ions available from weak acids. So depending upon the end point of acid-base titrations, we have to select the indicators. This point is very, very important. Depending upon the end point range for the titrations, we have to select the indicators. So in the titration of weak acid and a strong base, the pH range near the endpoint is 7 to 11. Since the pH range is endpoint is 7 to 11, methyl orange cannot be used as for such titration because the range of methyl orange is 3.1 to 4.3 only. So that's why it will not show any effect on this indication. So that's why we'll use phenolphthalein as well as thymol blue are the suitable indicators because they can show the pH range of 8 to 9.6 and 8.3 to 10. And what is the observations? What is the observations we have? We have the observation that phenolphthalein for acidic solution it is colorless and for basic solution it is yellow in color. So very, very important these indications and titrations. Please note it down. Next, selection of indicator for strong base. and weak acid. Slowdown of pH change due to buffer formation takes place, which is maximum pH is equal to pKa. So near equivalence point, pH again increase fast due to salt formation. After equivalence point, pH changes due to presence of strong base. So this is called titration of weak acid by strong base. So the pH changes will be from 8.5 to 11. So definitely we'll use phenolphthalein as an indicator. Phenolphthalein, this graph is also important. So phenolphthalein as an indicator. Next continuation. Weak acid and weak base. This is the titration pH, no range, no shape change. So that's why no indicator. So no indicator is used for weak acid and weak base. No indicator. No indicator is used, can be used for weak acid plus weak base titration. So this point is very, very important. No indicator can be used for weak acid and weak base titration. So this is the pH range. No shape, no change. No shape change. Now, titration of 50 ml of 0.1 molarity H3PO4 against 0.1 molarity NaOH solution is taking place. Calculate the pH when volume of sodium hydroxide is added. So when sodium hydroxide is added to 100 ml of first, second case 125 ml, third case 150 ml, fourth case 200 ml, fifth case 590 ml. So in all the cases, the pKa1 is equal to 3, pKa2 is equal to 3, 7, pKa3 is equal to 11. So for phosphoric acid, they have given it is 3. For sodium hydroxide, they have given neutral solution it is 7, and pKa2 it is given as 11. So we have to use calculate the pH when volume of sodium hydroxide added to 100 ml for this solution. 100 ml. So 50 ml and 100 ml of sodium hydroxide. So 50 ml of 0.1 molarity phosphoric acid again is 0.1 molarity, 100 ml of 0.1 molarity sodium hydroxide. So if you do that, you have to get pH value. So first case I will tell you. First case, so pH is equal to pKb plus log of concentration of salt by concentration of base. They have given concentration, that is salt concentration and base concentration, that is equal to pKb plus log of molarity into volume of salt by molarity of base into volume of base. You have to multiply like this. Then you'll get pKb, sorry, pH values. So this is for your understanding. So I'll give it as homework for you. So please try to do these problems, then you can understand better. So next, now we have completed successfully the indicators, common indicators. Next, we are going to discuss new concept. That is this concept, this chapter is over. So ionic equilibrium explanation part as well as numerical parts we have done successfully. Now we'll see some questions based on this today's concept, that is indicators. Then we'll do summary of the topic and we'll end the chapter. So please listen carefully. Yes. Write down the question. I'm writing here the question also. An acid-base indicator has, question number 1, an acid base indicator has Ka value, that is dissociation constant or ionization constant value 10 to the power of minus 5. The acidic form of the indicator is red. The acidic form of the indicator is red color, and basic form is blue, and basic form is blue. Which of the following statement is are correct? Which of the following statements? Which of the following statements? Following statements is are correct. It can be more than one correct option also. Is are correct. Option A. At pH is equal to 4.52. At pH is equal to 4.52. Solution is red. Solution is red color. Option B. At pH is equal to 5.47. Solution is blue. And third point, at pH is equal to 6. Solution is 75% red. And fourth option, at pH is equal to, usually you may not get this type of questions, but still, as we discuss this concept, only theoretical questions you will get. Solution is 75% blue. Solution is 75% blue in color. So out of these 4 statements, which is the right statement we need to tell. So let us see the solution now. I'll write it on the screen. So please note it down. This type of questions you may get. So now for this, the solution is I'll write with blue ink so that it will be more visible. HIN, that is indicator, indium, which is a red color, it is red in color, changes to H plus and IN minus. Since we have already seen this in slides, IN minus. So IN minus is blue color and H plus. So pKa, they have given pK is equal to, so since for this Ka is given, so pK becomes 5. pK becomes how much? It is equal to 5. So when pH is less than pKa, pH is less than pKa, color of acid form, that is red, predominates. Color of acid predominates, that is red color, predominates, that is red color. So at pH is equal to 4.52, solution is red color, so it is less than pK value. So first option is correct. Now let us see second option. Let us verify with second option. When pH is greater than pKa, when pH is greater than pKa, for this I'll write here, when pH is greater than pKa, color of basic form, color of basic form predominates. So blue color is formed. What is the basic form of this acid? Blue color. So blue color is formed. So at pH is equal to 5.47. 5.47 means is greater than pH is equal to 5 pK value. So second statement is also solution is blue. Second statement is also correct. And third and fourth statements are wrong by taking concentration of HIN plus and IN minus. So by taking concentration of IN minus by HIN plus concentration of HIN, we can say it is equal to 0.75 by 0.25 because 75% is given. So which is equal to 5 plus log 3, that is 5.48. 5.48 pH is equal to, for this case. So for this case, pH is equal to 5.48. So solution 75% rate is wrong. When pH is equal to 5.48, the solution is 75% rate. Similarly, when pH D is also wrong statement. So A and B is the right answers and C and D are wrong statements. It is around 7.62 and the solution is 75% blue. But here they have given exactly 6 solution 75% red. It is wrong. So when pH is greater than pK, color of basic form predominates, so blue color. So as pH is greater than pK at this position, that is 5.47, and pK is only 5. So that's why since pK is equal to 5, how we got pK is equal to 5? Because Ka is equal to 10 to the power of minus 5. So pK becomes minus log of 10 to the power of minus 5. It is equal to 5. So like these questions you may expect for IIT advanced level only. For mains level and NEET level, they'll just ask only the color indications and equivalence point and end points. So with this, we have successfully completed. So like these questions you may expect, as this contains, as this from this concept, you'll get very less number of questions. That's why I am not discussing more. So now we'll finish up this and then we'll go for summary of the chapter. After that, we'll wind up this chapter. Now, summary of the chapter, if you take into consideration, summary of the ionic equilibrium, very, very important. If you see the summary, I'll just clearly explain to you. First point, first topic in this chapter, various theories of acids and bases. Various theories of acids and bases. So we have, what are the theories of acids and bases? We have Arrhenius, comma, Bronsted logic concept, and Lewis theory. So from this, you may expect question from Bronsted logic concept and Lewis theory. So from this, you have to consider both questions based on Bronsted logic concept, that is conjugate acid base pair. What is conjugate acid for the given substance? What is conjugate base for a given substance? And which of the following is a Lewis acid? Which of the following is a Lewis base? Like that questions you'll get. Mainly these two, from these two theories, you'll get questions. So please work out questions based on Bronsted logic concept and Lewis theory. Second concept we have. So what is the second concept we have? Second concept we have ionic product of water. Ionic product of water, comma, dissociation constant of acid. Dissociation or ionization constant of acid, or ionization constant of acid and base. Ionization constant of acid and base. From this also you may expect question. Third point is pH problems. pH related questions. pH problems. Very, very important from third point onwards. pH. Fourth one, what we have done buffer solutions. Definitely you'll get questions from 3, 4, 5, 6. Buffer solutions. Very, very important. So less important and more important writing. Buffer solutions, definitely you'll get numerical or theoretical question. Next we have salt hydrolysis. Salt hydrolysis, which is also very important. Next we have questions based on solubility product. This is also important. Solubility product and sparingly soluble salts. Solubility product and solubility. This is also very important area. And finally, we have seventh topic. We have acid-base indicators. Acid-base indicators. So definitely you are going to get 3 to 4 questions for every competitive exam because it's a lengthy chapter and most important. Without any question from this chapter, there is no entrance exam paper. So please work out all these concepts clearly. What we have done in the section that is lectures, that is more than enough. Apart from that, if you could practice some other books, it is more better. So if you do questions based on this from other books, easily you can understand the concept and easily you can do. So this chapter is very, very tough. It is important for JEE mains as well as advanced also, and NEET also. So it is very, very important for advanced and NEET, JEE mains and advanced. Mains, JEE mains, advanced and NEET. So depending upon the level of exam, they'll frame a question. So these are the concepts in this chapter. So all these concepts are very, very important. Please do it properly so that you can do easily the questions in the entrance exam. So with this, I'm completing this lecture. So in the next lecture, we'll just come up with a new chapter. In next lecture, we'll come up with a new chapter. So do what we discussed in the lectures. That is most important. So with this, I'm ending this session. Thank you. Thank you all.